is 1D motion? Oh, thank you. I forgot to record. Okay. What is 1D motion? So it's just motion in one direction, basically, either horizontally or vertically. So some examples may be a ball being thrown straight up, a person diving straight down into a pool, and a person walking in a straight line. So you can only be horizontal or vertical. If you're going both at the same time, that's going to be called 2D motion. And you're going to go over it with that with Andrew tomorrow. But today we'll be only doing 1D. So only one at a time for today. All right. So let's try to represent position for a second. What you're looking at here is a motion diagram. Let's say this is Andrew. Okay, let's say this dot is Andrew. So you can see Andrew is walking along a number line with these numbers indicating meters. And every dot indicates a frame of 1 minute. So at this dot, the time is 0 minutes. At this dot, the time is 1 minute. And then this dot's going to be time equals 2 minutes, and then so on. So on and so forth. Okay. So from here, you can see that Andrew covers 100 meters from time is 0 minutes all the way to time equals 1 minute. Okay. For this interval. And he covers another 100 meters from 1 minute to 2 minutes. Okay. And then this is time equals 3, time equals 4. And then he ends here. So time equals 5. Okay. And then he covers 50 meters from 2 to 3 minutes, and then another 50 meters from 3 to 4 minutes. And then he covers a whopping 200 meters from 4 minutes to 5 minutes. Okay. So let's try putting this into a position versus time graph. What is a position versus time graph? It's just basically a coordinate axis with the x-axis being time, which in this case, the units is minutes, and the vertical axis being position, which is in meters. Okay. So here we have like a scaled down version of the diagram I just drew earlier. So how would this look like on a position versus time graph? Well, let's start plotting a few points first then, okay? So at t equals 1 minute, where is Andrew? Andrew would be at 100 meters, right? He would be here. So let's just plot a point here. At t equals 2 minutes, where would Andrew be? He would be, okay, this is t equals 0, t equals 1, t equals 2. He would be at 200 meters. Okay, let's plot another point. Okay, at t equals 3, where would he be? Where would he be? He would be at 250, right? Just smack right in the middle. T equals 3, he would be at 250. So let's just draw somewhere in the middle here. And then at 300, I mean, at t equals 4, where would he be? Where would he be? He would be at the 300-meter mark, right? So let's draw another dot here. And then at t equals 5. Okay, wait, this is t equals 3, this is t equals 4, and then this is t equals 5. Okay. And where t equals 5, where would Andrew be? He would be at the 500-meter mark, right? Let's just draw a point here then. Okay. Then let's connect these dots then, shall we? Okay. And those are the dots connected. And let's just assume between these intervals, he's walking at a constant velocity. So these would be linear, okay? So no acceleration here. It's just a constant velocity, but differing at some intervals. So what we can see here is when he is walking at a moderate pace, let's say from like from 0 minutes to 1 minute, it's like it's pretty steep, right? This line is pretty steep. Okay. But from t=2 to t=3, he's walking pretty slow, right? He's walking slower, and we can see that the slope or this line is a little less steep, right? It's a little less steep. And then, okay, wait, let's just mark it then. And then from t=4 all the way to t=5, he's going pretty fast, right? He covered 200 meters in 1 minute. So what we can see here is that the slope of the graph, or just basically how steep it is correlating with his velocity, right? Yeah. So wait, let's just erase some of this here. So what I'm trying to say here is that the slope of a position versus time graph is equal to the velocity. Okay. Let's just copy that. So from position to velocity, let's just paste that. Let's just paste that image real quick. Oh, it's not what I wanted. Okay, wow, it's not letting me. Okay. Uh, okay, well, so what I'm trying to say here is that the velocity is the slope of a position versus time graph, right? What is the slope again? Slope equals rise over run, right? What is the rise in this situation? That would be the position, right? In meters. The change in position, really, actually. So it would be delta x. We use this triangle to symbolize change in. So actually, delta x equals the final position minus the initial position, which is basically change in position. And yeah, if you guys have any questions, feel free to ask. Please interrupt me or ask Andrew. And the run here is it would be time, right? So it'd be change in time. Add another delta t. Okay. So slope equals the slope of this graph would be equal to change in position over change in time. And what does this remind you of? What does this look like? Oh, right, the formula for velocity, right? Velocity equals uh change in position over change in time, right? Or you can just say d over t, right? So here we prove that the slope of a position versus time graph is equal to the velocity. Okay. Make sure I'm not missing anything here. Okay. Uh, why do we use delta? Okay, remember delta is signifying the change in position. Okay, so if I just wrote an x, that would just say position. Okay, that would just be like a singular point of position. But if I do delta x, then it would be change in position. So I would have to do final position minus initial position. Okay. All right. Let's move on then. So how would that position versus time graph look as a velocity versus time graph? So wait, let me try copy and pasting that thing again. Oh, okay, wait. I can't do that then. All right, never mind. Let's just go back and forth then. It's fine. So how would that look like on a position versus time graph as a velocity versus time graph? Okay. So let's just try finding the velocity for these time intervals then. Okay, so now we know that velocity is the slope of a position versus time graph. Let's just find out the slope then. Okay, so from here it's from 0 to 2. This is a straight line. So let's just find the slope of that. So from t equals 0 to t equals 2, what is the slope? Remember v equals change in x over change in time. And what is, okay, x final minus x initial. And delta t would also be t final minus t initial, right? So let's just find that using the graph then. So from t equals 0 to from t equals 2. T equals 2. Am I missing something? No, I'm not. Okay. So from t equals 2, Andrew is at 200 meters. And initially he is at 0. And he ends at 2 minutes. He starts at 0 minutes. Okay, so the slope would be 100 from t equals 0 to t equals 2. Next interval would be from 2 all the way to 4, this straight line. Just do that quickly again on the side. So he starts at 200, right? But he ends at 300. And then from 4 minutes all the way to 2 minutes. So it would be 100 over 2, which would be 50. Oh yeah, don't forget units. This is also 100 meters per second. This is 50 meters per second. And then for this final section, he would be going the fastest, right? I think you can guess what his velocity would be. It's just basically double his moderate one, which is 200. He starts at 500. He starts at 300 and then ends at 500, right? In a span of 1 minute, which is from 5 all the way to 4, which is 200. So his velocity here is 200 meters per second. His velocity here is 50 meters per second. And his velocity here is 100 meters per second. Okay. And this is all when there is no acceleration, okay? So you can only do this when there is a straight line on a position versus time graph. And if it's curved, then that means there is acceleration. If you see this on a position versus time graph. We'll go over that later if we have time later today. Okay. So from 0 to 2 minutes, we find he has 100 meters. He is 100 meters per second fast. So let's just draw. Well, that's not really accurate, but you get the idea. So from 0 to 2 minutes, he is 100 meters per second. Let's just draw a straight line, right? Because he is constant velocity from here on out. So from 0 to 2, he is 100 meters per second. From 3 to 4, I mean, sorry, from 2 to 4 minutes, he is 50 meters per second. And then finally, from 4 to 5 minutes, he is 200 meters per second, right? So that exact situation translated into a velocity versus time graph would look like this. Straight lines, remember, because there is no acceleration. Why do I keep seeing a notification? All right, never mind. Okay, let's move on then. So so after looking at that, right? Seeing that example, let's give you guys a try on this, right? So let's try converting this position versus time graph into a velocity versus time graph then. Okay. So you guys might want to copy this down on your notebooks or whatever, and this is quite special because remember, velocity is a vector, right? It can go in different directions. You can see here that the slope is negative, right? It's going down. Your position, you're going negative, right? So the velocity would be your velocity would be negative from 0 to 30 minutes. Okay. So I'll give you guys a couple minutes. Let's see if you guys can try to convert this position versus time graph into a velocity versus time graph. And it's okay if you guys don't know how, because just getting started. So does anyone want to give a shot at this? You can just tell me how you want me to draw the velocity versus time graph. Sorry, this is supposed to be velocity. Or are you guys not done yet? Arjun, want to give this a shot?
I was thinking maybe you could do from 0 to 20 minutes, draw a horizontal line at like negative 1.5 kilometers per minute.
Negative 1.5?
Yeah.
Okay, wait,
And from,
let's look at this together then. So we're trying to find the slope from 20 you say. Oh.
yeah. And then from 20 to 40 minutes, you can draw like a horizontal line at 0 kilometers per minute.
Okay, wait, I'm sorry. So this is a downward straight line from 0 all the way to 30 minutes.
Oh. Oh
Oh
wait,
yeah,
shoot.
yeah. I don't I'm sorry if that wasn't clear. Is that clear to everyone? I should have made it a little simpler actually. Okay, wait. So it's a downward straight line from 0 to 30 here, and then a straight line from 30 to 50 here, and then an upward line from 50 to
Wait, what
80.
did you say? I didn't get it. Can you like repeat it?
Okay, so there's a straight line from there's a straight line that points down from 0 to 30 here, this
Yeah.
point, and then a straight line from 30 minutes to 50 minutes here, and then a line that points up from 50 to 80 minutes here. Got that, Arjun?
Yeah.
Okay. I can't really erase that. Oh well. Okay. Okay, any other takers? Or you guys might not be done. Leo, want to give this a shot?
I think there's a slope of -1 from 0 to 30 minutes,
Yeah.
and zero f- zero slope from 30 to 50 minutes,
Yep.
and a slope of, let's see if it's
Let's draw this in red actually.
1.5, I think, from 50 to 80 minutes.
Yes. Okay. Well done, Leo. That is correct. Yep. Okay. So for those who did not understand how we got to this point, I will walk through it really quick. Okay. So on this downward straight line, right? Let's find the slope of that because we know that is the velocity. Wait, hold on, guys. Uh, Never mind. Okay, so this downward straight line, let's find the slope of that because we know the velocity from 0 to 30 minutes then. Okay, so they start at 10. Okay, wait, no. They end at -20 meters. I mean, sorry, -20 kilometers. And then they start at 10. Oh, wait, I should probably write down the formula actually. Okay, so final position at 30 minutes is -20. Initial position at 0 is 10. And then final time is 30 minutes, and then they start at 0. So it'll be -30 over 30, which is -1, which is our first velocity here from the time interval to 0 to 30 minutes, which is correct. And then this straight line here, there is no change in position, right? There is no change in position. He just stays at -20 kilometers, right? So the velocity here would be 0 because he's not going anywhere, okay? So that is also correct. This is also correct. And this final line here, it's going up, right? So the velocity would be positive here. It's going up. So velocity, let's find it then. He ends at 0, and then he starts at -20 in this interval, right? And that's in the span of from 50 to 80. Yeah. So two negatives make positive. Okay, wait, actually it would be 2 over 3. My bad. I think 0 to 20 and then 50 to 80. Okay, it's not, it's actually not 1.5. It's actually 2/3. Hey, sorry if this graph is not clear. It's kind of goofy. Okay. So this is at the 50-minute mark. And then he ends at 0 at the 80-minute mark. Okay. So here, yep, we transformed a position versus time graph into a velocity versus time graph. Okay. Anyone have any questions? Okay. And another important concept, the area under a velocity versus time graph is equal to the displacement of the object, okay? Might want to write this down. Why? Let's do a simple example then, okay? So let's just draw a quick graph. Okay, let's say, I don't know, 5 meters per second, I guess. And then this is time in seconds, so that's the most simple. Okay, and then let's just say the object is going at a constant 5 meters per second. So it will just be a straight line. Okay. Okay. So the area under this line all the way to the x-axis would be equal to the displacement of the object. So let's find the area then, ending at 5 seconds. Oh, I accidentally erased that. So from 0 to 5 seconds, what would his displacement be? It would be the area under this graph all the way from 0 to 5 seconds, right? So let's find the area. But actually, no, sorry. So what is this area that we're solving for? It would be the velocity times time, right? Because that is the area of this rectangle. What is velocity times time? What is velocity times time? That would be distance, right? That would be displacement, actually. Displacement. So delta x. We can actually transform this into the formula for velocity, which is displacement over change in time. Oh, wow. Right? The area under a velocity versus time graph is actually equal to the displacement of an object, right? So what would the displacement of this object be then? It would just be 5 times 5, which is 25 meters. Okay. And you can also see this through units because we're multiplying meters per second with seconds, and the seconds cancel out, which equals to meters, which is the unit of displacement. Okay, so remember that the area under velocity versus time graph is equal to the displacement of an object. Okay, what if the velocity is negative? Well, then the displacement would also be negative, right? Think about it, right? If you're just calculating the area, and there's also a straight line from 0 to 5 seconds. And you wanna calculate the area from this line to the x-axis going up, right? So it would just be negative 5 times 5, which would be negative 25. Or just in the opposite direction of where you're going, if the problem gives you direction, okay? Yeah, okay. Anyone else have any questions? Okay. It's just the area under the curve, okay? But if it's negative, it's from the curve up to the x-axis. No questions? Okay, let's move on then. Okay. Let's introduce you guys to the concept of acceleration. What is acceleration? Acceleration is just how fast velocity is changing. Okay. So what is the formula for acceleration? Acceleration is just equal to the change in velocity over the change in time. Okay, as seen from this formula. It is a vector quantity, so it can be positive or negative with direction. And for Intro to Physics, all the way up to AP Physics 1, acceleration for any type of problem will always be constant, okay? It will be constant. So, because if your acceleration is changing, then you have to go into some weird calculus stuff. So, and we don't want that. So, acceleration for now will always be constant, okay? Uh, yeah, okay. So remember, A equals change in velocity over change in time. What do I mean by that? Well, I mean, delta V is final velocity minus initial velocity over final time minus initial time, okay? So triangle indicates change, okay? Okay, how would you get acceleration from a velocity versus time graph, right? Okay, let's recall then. Let's recall. We got velocity. How did we get velocity from a position versus time graph? We got it from the slope, right? From the slope. Okay, so how would we get acceleration from a velocity versus time graph? It would also be the slope, right? It would also be the slope. Why? We can prove it, right? We can prove it. So here we have a simple, let's just draw a simple coordinate axis. So what is the slope of a graph? Let's just draw a straight line. Slope equals rise over run, right? What is the rise here? It is velocity. Change in velocity. What is the run here? What is the run? It is time, right? It is change in time. Oh, what is that? What does that look like? Oh, that looks like acceleration, right? That looks like acceleration. Okay. And we can actually prove one of our kinematic equations from this, actually. So A equals delta V over delta T, which is equal to this. Okay. Actually, we can keep the T as delta T. Let's multiply both sides with a delta T. So it would be A times delta T equals V final minus V initial. And then let's move the V initial all the way to the other side, sorry, by adding a V initial to both sides. So it would be V final equals V initial plus A times delta T. Okay. So you guys will be actually using that equation in some problems we're going to do later. Okay, so these are our list. These are 4 kinematic equations you guys will need to know for Intro to Physics and Physics 1. So, and then later physics classes, you guys will need to know this. So actually, not the 4th one. Actually, screw that. You guys don't need that. Okay. So you guys will need to remember these 3 basic kinematic equations. Please write them down. We call this one Big Dog. We call that equation big dog. Why? Because it can do a lot of things. Okay. Almost using every kinematic question you can get. Okay, so write this down, please. You can prove these, but for the extent of our classes, I don't think we'll need to. But we did prove the first one though. So, okay, is everyone okay? Everyone's fine. No questions. Okay. Let's move on then. And I will also introduce you guys to the concept of free fall. What is free fall? So when an object is under the influence of gravity and is in air, it will experience a constant downward acceleration of 9.8 meters per second. Okay. And mass does not matter here. Mass does not matter. Any object will have the same acceleration in free fall. Okay. But you guys may wonder, it's like, so you know how a feather would fall slower than a bowling ball, right? Feather would fall slower than a bowling ball. But they both have the same acceleration. But then how would the feather fall slower than the bowling ball? Is because of other forces called air resistance, right? Air resistance. So the feather would obviously fall slower, right? But in our cases, most of the time in problems, air resistance is neglected. We don't care about air resistance. So actually in a vacuum of space where there's no air, if you drop a feather and a bowling ball at the same time, it's going to reach the ground at the same time, right? Because they're both experiencing the same acceleration, okay? But there's no air resistance to slow down the feather anymore. So that's why they're going to have the same, they're going to reach the ground at the same time, right? Okay. And this is when an object is in the air at any time, okay? So it doesn't matter when it is in the air. So if I throw a ball, right? If I throw a ball into the air, right after it leaves my hand, it's gonna be subject under free fall, okay? It's gonna be in free fall. The second it leaves my fingertip, it's gonna be in free fall, okay? It's gonna experience a downward acceleration. A down acceleration. Oh, why can't I? Can't draw anymore. Wow, okay. This app sucks. Alright, anyways. Uh, the moment the ball leaves my fingertip, it's going to experience a downward acceleration of 9.8 meters per second towards the ground, okay? Oh, my bad, guys. I'm going to have to do something here. Probably gonna have to make another copy, probably. Sorry, guys. It's gonna take a couple minutes. Oh. Oh, wow. Okay. Well. mm, Okay. Well, I think we're gonna have to use this then. Okay. Yeah, back to free fall. If a ball is in the air or any object, uh, it's going to experience a downward acceleration of 9.8 seconds, okay? No matter what, no matter what. If it experiences no other forces. Let me move on. Okay. So let's answer some conceptual questions about free fall then, okay? So a ball is thrown straight up into the air. At each of the following instance, what is the ball's acceleration? Okay.
Is he guys lagging for you guys as well, or
Yeah, he's lag.
Yeah, he's frozen.
yeah, all right. Let me just yeah, all right. I'll take over for now. I apologize for the this app. Let me just text him.
Hi guys, my Wi-Fi cut out. Speakers. Wow, it's crazy.
The camera's still kind of.
Considering
Oh, it
Andrew
froze
also had bad
again.
Wi-Fi yesterday.
Yeah.
You're still kind of freezing. Uh,
Am I still freezing?
no, it's better now.
I'm freezing. It's better now? Okay, because I'm
Yeah.
using hotspot. Wow, okay. Yeah, the lights were flickering for a second. What the heck? That's crazy. Uh, should I continue then? I should continue. I should probably continue. Um, if there's a Wi-Fi on this thing, how is there Wi-Fi? I'm so confused. Okay, then you know what? It doesn't matter. It doesn't matter. Let me join back on the iPad then. Sorry, guys. Don't know why that happened.
Recording in progress.
Just do this, share content. I need to give my other thing co-host. Am I being laggy again?
Still kind of laggy.
Laggy? Let me try again. Oh. Okay, wait, I think my Wi-Fi came back. Am I fine now?
Yeah. I'm still a bit laggy, that's fine.
Okay. I'll try talking a little slower then. So conceptual, back to back to this question. Ball is thrown up straight up into the air. At each of the following instance, what is the ball's acceleration? Any takers?
Wait, I have a question.
What? What's up?
So, like, the acceleration is like increase in speed, right?
Increase in speed, yes. Change
So
in
that means like
velocity.
if it's like like if I throw it, if I throw the ball, like then it'll stay the same speed until it reaches the top, and then that's when it's gonna accelerate. So can it be at the very
Mm,
top?
Okay, wait. Okay, that's actually a really common misconception of acceleration. So let's just draw a diagram, right? Let's just make this more clear. Okay. Oh, that's a whole, I don't like this app. Okay. Just draw a diagram. This is a ball. And this is it being thrown up, right? Let's just draw some arrows. This is the top of the thing, and it starts going down, right? So the moment it leaves my hand, it's going to experience a constant acceleration of 9.8 meters per second squared towards the ground, okay? So it's going to experience at any points in this time of travel, it's going to experience an acceleration towards the ground. No matter if it's going up or down, okay? Doesn't matter. It doesn't matter. It's in the air, okay? Why? Well, you can see this ball. You gave it an initial velocity going towards up, right? But why is it curving down? That's because it's experiencing the acceleration towards the ground, right? It's experiencing gravity towards the ground at a 9.8 meters per second, right? So it doesn't matter. It as soon as it leaves your hand, even if you throw it upwards, right? It's gonna
So like
the velocity is gonna start decreasing, okay?
so like basically so it starts experiencing like the gravitational pull and the constant acceleration the second it leaves because but like even if it's going up,
Yeah, yeah.
it just takes a while for it to start coming down.
Yeah, because you gave it an initial velocity of, let's say, 10 meters per second going up, right? But your oh no, let's say let's make that bigger actually. Give it 50, okay? Let's give it 50 meters per second going up, right? But then your acceleration goes going towards the ground is a equals negative 9.8, right?
Yeah.
So when it starts going down, the velocity is going to be negative, right? Because it's going down.
Yeah.
So when it's up at this highest point, it's going to be at 0 meters per second. Okay. Because imagine, right? It's going up, the velocity is positive, it's positive, it's positive, and then it finally reaches 0, right? But then it's still under gravity, right? It's still going to experience that negative 9.8 meters per second squared.
Yeah.
And then it's going to finally start coming down, right? The velocity's okay, you like imagine you're constantly taking away from this velocity, right? So at this moment it's 50 minus 9.8, and then later it's going to be I don't know, around 40 minus 9.8 again, and then it's going to be 30 minus 9.8 again until it reaches 0, right?
All right.
And then
Oh,
yeah, that's when it reaches the highest point, and then it's still under gravity, right? So and then it's gonna become 0.9. It's gonna be that, and then let's round that to 10. It's gonna be 9.8 again, right? And then it's gonna keep doing that until it hits the ground, right?
oh, okay. Yeah.
Okay, do you get it now, Arjun?
Yeah, yeah.
So it doesn't matter if if you throw it up, it's still under the concept of gravity, right?
Yeah. All right, I get it.
Okay. And yeah, okay. So Ani, for your question of why 9.8 is just because of the Earth, okay? We did a lot of tests. Scientists did a lot of tests. It's just that number. It's going to be different for different planets, right? Because the gravity of different planets are different. So on Earth, the acceleration towards the ground is going to be 9.8. But for example, on the moon, right? The moon is smaller. So the gravity of the moon is a little weaker, right? So the gravity on the moon towards the ground, the acceleration towards the ground is actually going to be 1.6 meters per second squared, okay? So 9.8 is just for Earth, okay?
Okay.
All right, let's move on then. I don't like how it erases everything. Okay, so I think we're running a little low on time then. So at each of the following instances, what is the ball acceleration? A, just before leaving your hand, it's going to be 9.8, right? It left your hand, okay? So it's going to be 9.8 meters per second. At the very top, it's still in the air, right? It's still in the air. It's still experiencing that gravitational pull. It's still going to experience that 9.8 meters per second squared. Just before hitting the ground, it doesn't matter, right? It's still in the air. It's still going to experience that 9.8 meters per second squared. So it's all the same. It's in the air, and there's no other forces acting on it other than gravity. It's going to get that 9.8 meters per second, okay? Here is another question. A rock is thrown, not dropped, straight down from a bridge into the river below. immediately after being released, is the magnitude of the rock's acceleration greater than g, less than g, or equal to g? And immediately before hitting the water, is the magnitude of the rock acceleration greater than g, less than g, or equal to g? Sorry, g is gravity, so 9.8. Yeah, we usually use g to signify the acceleration for gravity. Any takers? Arjun.
I was thinking that like so immediately after being released, it's probably gonna be equal to G.
Yep, that's correct, right? It's in the air. No other force is acting on it, right? Your hand left us, so it would be 9.8, yeah.
And then for the next one,
Oh,
it's
sorry, this
gonna
is supposed
be
to be
it's gonna be greater to G, I think.
greater than g? Why?
I mean no, less
What do
than
you
G,
mean?
less than G.
So, okay, wait, let's reinforce the concept of gravity, right? So, actually for this question, it would be equal to g still. Okay, still equal to g, okay? So, the acceleration is sorry if I didn't say this. Acceleration, it's constant. Okay? The acceleration is constant. This is gonna stay
So
true.
wait, so
So
it's
it's
the same
still
speed the whole time?
yeah. No, not the same speed, it's the same acceleration, right?
Yeah.
Acceleration equals the change in velocity over the change in time, right?
Yeah.
But this acceleration is constant because of gravity, right? Gravity doesn't change. So we're talking about the acceleration here.
All right.
So it would be the same. It's still equal to g. It's still equal to 9.8.
Wow.
Okay.
Wait, because
So
it's going at like a constant acceleration, so it's gonna be like equal to that. So it's gonna be like falling down at the same like acceleration the whole time.
yeah, it's gonna have the same acceleration towards the ground at any point of a projectile's travel path.
All right.
But the velocity is changing, right? Because there's acceleration. Because acceleration is a change in velocity. Yes, Ani?
Would there ever be a case when it would be greater than G or less than G?
For a object in the air?
Yeah, or like just before hitting the ground.
No, it would always be equal to g. Okay, it would always be equal to g. Why? Because the only okay, so you guys will learn this on Thursday with me, but what causes acceleration, right? What causes acceleration? Forces cause acceleration, okay? If the only force you're experiencing is gravity, your acceleration is going to be constant, okay? So as you can imagine, as a projectile going down towards, right? The only force you're experiencing is gravity, okay? And since you're only experiencing that force, and that force is constant, your acceleration is also going to be constant, okay? You got that, Ani? So there's like if there's no other if there's more forces acting on the object, then yeah, the acceleration is going to be different. But in the case of projectiles, it's always going to be under the influence of gravity and only gravity. So the acceleration is always going to be 9.8, okay?
Okay.
Okay. Yeah, we don't have a lot of time left, so let's try to do one kinematics problem, shall we? Let me move on. Okay. Okay, let's go through some 1D problems. A car is traveling at 25 meters per second when the driver sees a red light and applies the brakes. The car comes to a stop after 5 seconds. What is the car's acceleration? So basic rundown of how to do 1D kinematic problems. Let's try to identify what we have first, okay? So a car is traveling at 25 meters per second. That is our initial velocity, right? So we know that. Okay, our initial velocity is 25 meters per second. The driver sees a red light and applies the brakes. The car comes to a stop after 5 seconds. Okay, so we know the duration, we know the time. Okay, we know the time. So time, delta t is equal to 5 seconds. Okay, and okay. But we need to find the acceleration. Okay. If you wrote down the kinematic equations, like, can you guys try to find an equation that has these variables? Oh, sorry. We forgot one more variable. The car comes to a stop. Okay, a stop. What would your velocity be if you stopped? Your final velocity would be 0, right? You stopped, right? So your final velocity is 0. Okay, so we know these 3 variables. We want to find A. We want to find acceleration. So what equation has these 4 variables? We know these 3, so we can solve for the last one. Arjun,
I know the answer, but I don't know like the equations.
the equations? Okay, so it'll be the one I proved, right? It would be final velocity equals initial velocity plus acceleration times time, right? It would be this one. Yeah, that is the first kinematic equations you guys need to know. So wait, then how do you know the answer if you don't know the equation?
No, cause like I kind of just use like context. Like the car's acceleration would be like -5 meters per second because he's slowing. Cause like if he comes to a stop after 5 seconds, then you would do like 25 divided by 5 seconds, which would be 5 meters per second, and then that means he'll be slowing down 5 meters per second every second.
Oh, okay. Well, that's pretty smart. Okay. Well then, okay, but we need to know, like, you can't do that for every question, right? So we need to know how to do these with the kinematic equations. So let's just plug these in, right? We know final velocity. What the heck just happened? It just erased all my things. That's not very nice. Okay. Just write it again then. Okay, we know final velocity is 0, right? You came to a stop. Initial velocity, they gave us that, right? 25. And acceleration, we want to find that, right? So let's just leave that as the variable A. And time, how long does it take? It took 5 seconds, right? Okay, so let's just solve for A then. So A times 5, let's move the 25 over to the other side. So it would be A5 equals -25. And then you divide both sides by 5, right? So it would be -25 over 5, which is -5 meters per second squared, right? So that would be the answer. It's negative, right? Because you're slowing down. You're not speeding up, right? You're slowing down. Okay. Yeah, I think we kind of ran out of time today, guys. Sorry. I had some more problems for us, but let's move on to the summary then. So, why? Okay. Summary. 1D motion, remember, is motion in either horizontal or vertical direction. A position versus time graph plots the position on the vertical axis against time on the horizontal axis. And remember that velocity is the slope of the position graph, okay? Remember what a velocity versus time graph is, and that acceleration is the slope of a velocity versus time graph, and that displacement is the area under the velocity graph. Next slide. Free fall. Remember, when you're in the air, the only force you're experiencing is gravity. So your acceleration caused by that force is always going to be constant, okay? Because that force is not changing. So it's always going to be a downward acceleration of 9.8 meters per second, okay? And acceleration is just how fast velocity changes, okay? And it'll always be constant for now, okay? It will always be constant in problems, okay? Just how this 9.8 meters per second is constant as you fall through the air, right? Okay. And I think if you guys want to do this as homework, you guys can. But we didn't really go through all the equations, how to use them yet. So I'm not sure if you guys want to try this, but if you guys want to give it a shot, nice you can. If you want to take a picture or you want to write this down. Remember all the kinematic equations. Guys need to know that, especially for tomorrow's class. And yeah, I think that'll be it for today. You guys for joining, and Andrew will see you guys tomorrow.
Bye.
Wait, guys, if you have any
Bye.
questions on today's lecture, you guys can stay back and me and Adam will answer any of them, like any clarifying questions.
Sure there's a lot of questions still, but
Thank you.
bye guys.